And I know my daughter works for Ernst & Young, and this is what they have. It's a little thing, and you've seen this also. You ever see this thing where they go, type in what you see, and some strange thing? You know, like it says, fat barracuda. It has no sense whatsoever. But you type it in. The problem with those is most of the time you can't read it. You know, like, but that's time.rsa. What they do is they give a random thing that they turn into a word based on RSA, and you have to match it. On my daughter, it's actually to get into her Ernst & Young account. So there's a little thing here that flashes random numbers. And to get in, you need the password and those random numbers. And the chance of, you know, picking the right random numbers is 0, really. So, okay. Now, that's one. So there are many solutions to this. Now, what we're going to do is we're going to present an alternative. And the alternative uses combinatorial group theory. And in particular, it goes back to Wagner-Magyaric. It solves the repeat problem, the challenge-response methods, by using the difficulty of solving the word problem without knowing a group presentation. Now think about that as a problem. Suppose that I give you 2 words in 2 different alphabets. And the question is, do they represent the same element of some group? But I never tell you what the group is. The group is a shared secret of the communicating parties. So this is a symmetric key. So Kadi and I get together and we agree on a group that has a presentation, and I'll make this precise in a moment. It has a presentation. Yeah.
So do you have to know that the word problem is solvable?
Yes, yeah, that's one of the things. But we pick a group out, and it doesn't even matter if the word problem is difficult or not difficult in this. So Kadi and I get together and we choose a group. Okay, and we'll see, I'll make it precise in a moment. It's called the challenge group. And that group has a solvable word problem. That means given a word you can tell it's the identity, or equivalently, given 2 words you can tell if they're equal. And what we're going to do is the challenge questions are going to be, are 2 elements equal or not? Now it can't be that simple, because then it's a 50% chance of hacking in if the answer is just yes or no. But we're going to further assume, and just for the people who know a little more, that the groups have normal forms. Normal form is a fixed thing. And what we're going to do is, the bank is going to send you a word or the verifier. You're going to put it in normal form, send it back, and the bank checks if you did it correctly. And think about that. If you don't know the group, you don't know the presentation, how would you write the normal form for the group? So that means that you have to steal not only the password, but the group, which is harder than stealing just a bunch of answers. Yeah.
But how many people know group theory?
Well, that's always the argument on all of the group-based cryptography. Isn't that part of the difficulty of the problem? Yes. So.
But all crypto systems are group theoretical, even RSA. So
yeah, well, that's what I said at the beginning.
Yeah.
That's what I said at the beginning. But the fact is, there's more people who can attack a number theoretic crypto system than can attack. Like, we have a crypto system that we've been trying to write up now, Gilbert and I, that someone believes that there's a Grosvenor basis attack to this crypto system. Well, 1 person in 5 million knows what a Grosvenor basis is. So how many people?
Now with all the unemployed mathematicians these days.
Yeah, now they know. But the fact is, if there is, you can hire one of these people. Now this crypto system has the following features. Number 1, it's based on what's called the group randomizer system. I'll explain that in a moment. Number 2, the group randomizer system is a subset of what's called MAGNUS. And MAGNUS, many of us know, is a much larger computer algebra system. It was developed at City College, at Case, and it handles algorithmic problems. Now the thing is, the group randomizer system is a subset of that, so it's a much smaller program. That's important because you don't want to transport the whole MAGNUS program into a computer thing, although it's not that large. Now the group randomizer system works We're thinking of this backup system as going computer to computer. But we've also developed it on a PDA. So you can go to the bank and you have it here, and your randomizer system is in the PDA. Okay, now, that's one feature. Second feature is, the theoretical basis of this is the theory of finitely presented groups, in particular the difficulty of solving the word problem. And the theoretical security, and this one, it has a provable security that I'll give at the end, is based on the theory of equations over free groups and something called the strong generic free group property. So let me get into what it is. Now, this is the advantages of this. We're going to call the password presenter. This is standard language in cryptography, the prover. And the person who gets the password is the verifier. In the original version, we have a paper on this. The original version, I wanted to call it user and bank, to think of this as going and using it in a bank. But the referee wanted me to use standard language. Okay? So the person giving the password is the prover, the person checking is the verifier. Now each user is assigned a finitely presented group called the challenge group. And we'll assume that both the prover and the verifier have a device that has the group randomizer system in it. Now, what does a group randomizer system do? It verifies to the prover, to the verifier, but at the same time, and simultaneously, it verifies the verifier to the prover. So it's two-way authentication automatically. So you don't have to ask the bank any questions. It goes back and forth. Each login, this is what makes the security. Each login, and I'll try to make this specific in a moment, is essentially a one-time keypad. It's like a random one-time keypad. Each thing in. And it's not, because it's a random one-time keypad, it's not susceptible to either middleman attacks or repeat attacks. If the middleman gets between you and steals the results of a particular session, it's meaningless because the next session is completely random within the group. So what it boils down to is that an adversary or a thief has to steal three things. Has to steal A, your password, B, your challenge group, and C, the device. Now the device, they can always get their own device, so the device, but they have to have a device. There's no way to steal it by doing this by hand. All right, now, what are the basic features of it? Well, let's see. Well, it's an infinite supply. Let me go on. Now, the group randomizer system is a subset of MAGNUS. And what it includes depends on the cryptographic protocol, what we need. But in all of them, we have the following basic things. The group randomizer, and from the viewpoint of learning, say, combinatorial group theory, these are basic things that you learn in the very beginning. What's important is they're also not hard to program. And these were built into MAGNUS a long time ago. But the first thing it'll do is recognize a finite presentation of a finitely presented group, and it can rewrite words by the rules of the presentation. Okay, so if you're in a finite cyclic group, let's say of order 8, and the word is x to the 6th, it can rewrite it as x to the minus 2. That's a very simple example, but that type of thing, so it can rewrite it. Now, secondly, given a finite presentation of a group of a solvable word problem, it can recognize whether two free group words have the same value in that presentation. So what happens is it'll take a free group on something, it can rewrite it in terms of the generators, it can take another free group word, rewrite it, it can compare those within the group itself and say yes, they're the same word, or no, they're not the same word. And these, again, not hard problems to do. They're lengthy by hand, you can't do it by hand, but by program they're very simple. It can randomly generate free group words. Okay, so there's a method of randomization that, given an alphabet, it'll give you a random free group word that behaves like it's random. Fourthly, it will recognize and store free group words. Storing is going to be important because this is going to kill the replay, any replay attack. It can solve the membership problem. Now the membership problem is, given a set of words, that generates a subgroup, and some other thing, is it in there or not, and if it is, to rewrite it in terms of that. And finally, it can accept a random free group word and rewrite it in a normal form. Okay, now that's basically what the group randomizer can do. So now we're going to give several variations of how you can use the combinatorial group theory combined with the group randomizer system to do backup password security. And like I said, it's a very simple idea, but it works. So here it is. Here's the general outline. It's symmetric key. Now, symmetric key means that the prover and the verifier have to get together at one point. It's not public key. It's public key in the sense that an adversary can see it. We don't care if an adversary sees it after it runs. But initially, the prover and the verifier have to get together, even if it's just on computer, and verify their single private key. Now this is the feature. This is not a knock on this system. This is a feature of backup password systems now. You know, what do? When you start the whole thing, they say, please answer the following simple questions, and then they do it later. So if a thief can get in at the verification beginning, they can steal it at the very beginning. All right? Now, one of the problems, think about the thing is that your answers are encrypted, but the thief might steal your answer. Maybe they can figure out the encryption that's being used and steal your answers there. Do you follow what I mean? This is not susceptible to that at all. But, okay, so that's what we get. Now, next, we assume that both the user and the verifier have a randomizer system, and we assume that the adversary has access to the encrypted form of the transmission. But we'll assume that it's a passive adversary. So they're not changing the message. So we haven't examined, what are they called, ciphertext attacks, where they can randomly change the messages and see what happens.
That's the next stage.
That's the next stage, but I believe it's still not susceptible because you'll see from the outline. All right. Now, we start out, step one, the prover and the verifier communicate directly to set up a common shared secret. The common shared secret is a duple, a double, P and G. P is your standard password, like Sal1, and G is a finitely presented group. That's called a challenge group. It's a finitely presented group which has a solvable word problem and satisfies the strong generic free group property. I'll explain what that is later on. Okay? That's unnecessary in general, but we'll see. Now, step two. The prover presents the password to the verifier. So let's think of this as a bank user. The user comes, types in the password. What the bank does is send a question about the group back to the user. Question in quotes, because it's not a question, it's something about the group. Now the assumption is this question is difficult in the sense that it's infeasible to answer it unless you know the presentation of the group. Okay? There are many questions of that form, like what's the order, what's the center, and so on. So you get questions, but the question is about the group. Now, step three, okay, now, the point is, if the prover answers the question correctly, that verifies the password. Now, to prevent maybe a wild guess, the question's then answered, but this is repeated a finite number of times.